In today's video, we're going to talk about three things: the speed of sound as it travels through tissue, the definition of acoustic impedance, and also what acoustic impedance has to do with the different interactions that you can have of sound as it travels through tissue. So starting off, sound isn't like light. It doesn't have a constant speed. So as it is a longitudinal wave, the medium that it travels through is what impacts the speed, the physical properties of that medium. And so these are just a couple of speeds for common tissues that we look at with ultrasound. And you can see that most of them are right around the 1500 range. So most ultrasound machines actually use an average speed of about 1500 to calculate depth when they're forming an image. Try not to show you too many equations, but I think that this one's important. So one of the most important properties when you're looking at ultrasound is the acoustic impedance of the particular tissue that the sound is traveling through. And where there are changes in acoustic impedance is what is defined as an interface. And that's where most of the interactions that we're going to talk about happen, usually at interfaces between two tissues of different acoustic impedance. So what is acoustic impedance? Well, it's basically the product of the density of the tissue and the speed that the sound travels through the tissue. So moving on to talk about our interactions with tissue, the interactions that we're going to talk about today are three different types of reflection, in addition to scatter and also to attenuation. We're actually going to start here with attenuation, and as you can see with the animation, as the sound wave travels through the tissue, it's actually losing energy as it goes along, and that's represented in here by the size of the ball decreasing. And the reason why we have two different balls is because these are two different frequency sound waves. And so you can see that the red ball is a lower frequency, which is attenuated much less as it travels through the tissue, and the orange ball is a higher frequency sound wave that is attenuated faster as it travels through the same volume of tissue. So moving on to our next interaction, what we're going to look at is incident reflection. And I wanted to draw your attention to the designations down here, where it's showing us that tissue 1 is over here and tissue 2 is over here. And the orange bar actually isn't really a physical thing other than it's the interface between the two tissues. And so our sound wave is going to pass towards the interface. Once it hits the interface, it's actually going to reflect back a portion of the sound, and also a smaller attenuated portion of the wave is going to continue to propagate forward. Moving on, what happens if the tissue interface isn't directly perpendicular to the path of the beam? Well, that's when you get into the situation called off-angle reflection. So if we watch the red ball traveling towards the interface on this one, you can see that the sound wave is transmitted, but its path is changed, and the reflected sound wave actually does not go straight back towards the transducer, but is reflected off to the side. And so this particular off-angle reflection may give artifacts, but it doesn't necessarily contribute a lot to image generation. If you don't have a smooth interface between your two tissues, remember acoustic impedance number 1 and acoustic impedance number 2 over here, if you have a rough, kind of bumpy, spiky surface, what happens then is specular reflection, where the sound wave breaks into numerous smaller sound waves as it's reflected from this interface. Finally, probably the most important interaction with tissue is called scatter. And what happens is you have your sound beam that's emitted from your transducer, and it hits a tiny reflector and causes sound waves to be scattered off in numerous different directions, and that's what it's represented here by these two curved lines. The two dotted lines are showing you that over time those scattered echoes are reflected back towards the transducer. And so whether or not something is scattered actually depends on the particle diameter, and it actually has to be less than the wavelength. Scattered echoes and interference patterns from scattered echoes are predominantly what leads us to see the echo texture for things like the liver or muscle or kidney and how those are different. So scatter really is probably the most important tissue interaction for image formation. To summarize what we talked about in this video, we talked about the speed of sound as it travels through tissue and how the speed is dependent on the tissue type. We talked about one other physical property, the acoustic impedance, and how two tissues with different acoustic impedances form an interface between them. And that's where many of the types of interactions like reflection happen within the tissue.